Hi, and thank you for coming today. My name is Hailey Seago, and I'm a PhD student at the University of Oklahoma. Today, I'll be presenting my master's thesis from the Oklahoma State University titled Using GIS to Identify Suitable Areas for Sustainable Drainage Systems for Floodplain and Stream Channel Mitigation in Stillwater, Oklahoma. A little background before we get started today. Many of the United States has seen a stormwater sewer deterioration caused by urbanization, climate variability, and land use change. Much of this also contributes to a rapid discharge of precipitation through man-made and natural channels, which disregards soil moisture needs and the recharging of groundwater. So as the capacity of these standard stormwater systems is exceeded, there's also flooding. Many urbanized cities have been looking towards sustainable drainage systems, or SEDS. These restore the natural water cycle and mitigate flood risk. They use the landscape's ability to slow, filter, and absorb rainfall. They're also referred to as green infrastructures, and they include best management practices such as bioretention cells, bioswales, green roofs, permeable pavement systems, and rain gardens, as there are many more. As seen in this photo, it is Stillwater, Oklahoma during the flood of 2019 in May, where many of their outdated stormwater sewer channels were flooded significantly, as seen in this photo. So my objectives for this study are to locate stormwater infrastructure problem areas, identify suitable areas for SUDs, for SUDs, and create flood relief to floodplains and stream channels in Stillwater. I intend to show how tools in ArcGIS can be utilized by stormwater managers to identify flood hazard areas via spatial analytic technology and simulation models. Also, how urbanized areas can be retrofitted with SUDs, and how this demonstrates the alleviation of flood events, the efficient use of land, protection of stream channels and water quality, better management of runoff, and decreased impervious surfaces. And for the modeling section, using PC Swim of pre and post SUDS integration with GIS defined stormwater sewer infrastructure zones will also help stormwater managers see the economic, social, and environmental benefits of implementing such practices. So for my methodology, there was a data collection, GIS application, and then the PC Swim preparation. For the data collection, the city of Stillwater, Michek and Associates joined a contract with the Environmental Science Graduate Program at OSU to conduct an assessment on the condition of stormwater infrastructure and characterization of the stream channels within city limits. This is where I took qualitative data of stormwater structures like pipes, inlets, and manholes, and also looked at stream channels in the field where there were scouring of the banks, trees that have fallen in, sediment deposition, and other factors that could harm the condition of the streams or benefit the streams. But I use ArcGIS Collector, which is an app on the iPad I'm holding, and then a EOS positioning systems, which tracked my location. For the GIS application, layers were converted to be used in ArcGIS if they weren't already in the right format. And then other data that wasn't collected out in the field was retrieved from the USGS Geospatial Gateway. The city of Stillwater also contributed some data from the 2019 flood, and Michek and Associates contributed the information that I was collecting out in the field. Geoprocessing tools such as Intersect, select layer by attributes, clipping and converting layers was used, as well as adjusting the symbology. One common tool that I used in our GIS was the intersect. That helped me take different criteria, such as land use or the hydrology or the soils, and figure out where many of those intersect in the same area. The example I have here is where flooded streets and the FEMA hazard areas were in the same area. For the PC swim preparation, I took what I learned from the GIS applications, which helped prioritize suitable areas and helped me locate what the study site would be, which was Babcock Park. And then I was also able to take the flood prone areas that had characteristics for the sustainable drainage systems. And then also find what area would be most efficient. So that was all just to locate what the study area would be and what stormwater infrastructure and sustainable drainage system would be best fit for those areas. For the storm simulation, that was created using an SCS type 2 storm on a 24-hour time interval. And I ran 1, 2, 3, 4, 5-inch rainfall volumes on both pre and post SUDS implementation. And those storms were selected based off of the average rainfall experience in Stillwater, as well as the maximum amount of rainfall experienced. So my findings were separated into 3 sections, which was the flood prone areas, the suitable areas for SUDS, and then the PC swim simulation. So flood prone areas was a big one to see where a lot of water was setting in the city of Stillwater. So FEMA has their flood hazard areas, which the red is the 1% chance of annual flooding and a 26% chance of flooding over 30 years. And the yellow, there was the base floodplain, which at any given storm could flood. And the green was moderate to minimal flooding, except whenever there is a 500-year flood, it will flood. And if you see the black lines, the thicker black lines in those yellow areas, that is where flooding was occurring, especially during the 2019 event during May. Taking that layer and combining with what kind of criteria is needed for a sustainable drainage system, as well as what properties were already owned by the city of Stillwater, I was able to find these green suitable areas throughout city limits. I ended up going with Babcock Park, which is located in the lower part of the map with the star, and going with a bioretention cell was the best fit as sustainable drainage system to be implemented there. So in this photo, you can see the study area, which is Babcock Park. The green polygon is where the catchment for that bioretention cell will include, and it shows the pre-existing standard stormwater system that is in place, as well as a cross section of what that is. It was a 24-inch pipe. So for the PC swim simulation, running all 5 of those storms pre and post implementation, starting in the upper left-hand corner, there was pre 10,460 cubic feet of runoff compared to post was 0 cubic feet of runoff. For the 2-inch storm, it was 22,510 cubic feet. Post was 194.1 cubic feet. For the 3-inch storm, it was 28,360 cubic feet pre, and post implementation was 1,803 cubic feet. For the 4-inch storm, the total runoff was 37,860 cubic feet compared to post 5,137 cubic feet. And then for the total runoff of the 5-inch storm, it was 46,410 cubic feet and 9,853. cubic feet. As this SUDS implementation based off of the PC swim simulation can reduce the total amount of runoff produced by a 5-inch storm during a 24-hour storm event by 79%, according to the PC swim simulation. So getting to what environmental, economic, and social benefits of implementing a sustainable drainage system for this site. For the SUDS example, for this simulation, bioretention cell is used, which provides a wide range of benefits as seen in this slide. They also work as a small-scale wetland within these urbanized areas, so they're able to hold water for a longer time and collect especially water from parking lots or other impermeable surfaces, and the soil and plants help to trap that silt and pollutants collected from the runoff and helps that from getting into the stream channel. A good example that has been done as seen in this photo is from Milwaukee, where they implemented several bioretention cells close to a highway to help before that water reaches into the stream below. Another example is in Williamsville, New York, where they put a bioretention cell by a parking lot. They were able to significantly help water quality issues, and mainly with turbidity was their issue. Helps reduce that flow into the stream, and so there isn't the high flow events that are causing the stream scouring. The economic benefits, a good example came from Lancaster, Pennsylvania, where they helped them avoid $661,000 in pumping and treatment costs and $120 million gray infrastructure costs over 25 years. And it helped them benefit almost $5 million annually just by implementing their sustainable drainage system program. Not only does it help save money that way, but for landowners in the community, it decreases their property damage and costs. It also helps increase property value, create jobs, and there are several programs that cities and other municipalities can use to have money to pay for such projects. For the social benefits, research has shown that the willingness to pay for a home in a community with sustainable infrastructure and green spaces is on average higher than it is with a community without. Cities with sustainable drainage systems implementation have additionally reported an increase in outdoor activity, and that these areas create a green space for community to enjoy recreationally, which generally improves the overall health and well-being. It becomes a quality place for people to live, including the aesthetics and reduced noise population. Another benefit socially is outreach programs that can convince the community to implement more of these sustainable drainage systems, such as a rain garden, green roofs, or planting, and an educational component where people could come in and learn about these areas and why they're important to be implemented in their communities. So for the project that I just presented, the cost of implementation for a 3,000 square foot bioretention cell would be $36,451. Also, there would be a $45 per square foot site preparation and a $12 per square foot of materials. Other fees could include a planning fee, construction fee, as well as an annual maintenance worker, or if that was done by a volunteer. In conclusion, Stillwater can benefit environmentally, economically, and socially from the implementation of these SUDs. Climate variability and urbanization are predicted to increase problems in Stillwater's watershed and watersheds around the world. Real-world applications have proven that SUDS improve water quality and conserves water, strengthens the local economy, and builds community and infrastructure resiliency. Stillwater can use this study as an opportunity to integrate SUDS across several infrastructure improvement projects over a long-term plan. As seen, there were several suitable areas that could implement these plans from using ArcGIS as a tool, and that these projects can mitigate flooding and stream channels, like getting stream water quality improved to get them off of the 303D list. And the community of Stillwater benefits from the flood resiliency through decrease in property damages and erosion along these stream channels. Altogether, SUDS creates a contingency to reduce the cost of implementation and promote economic and sustainable friendly stormwater practices for the future. Thank you all for coming today. And if you guys have any questions, I'd be happy to answer. Thank you.